Hello everyone. Let's look at today's Leetcode problem 3373. Maximize the number of target nodes after connecting trees to. Before starting this problem, let us look at a motivational quote for today. When you focus on the goal, obstacles become the path. Most people stop when they hit a problem, difficulty, or any setbacks. Instead, embrace problems as stepping stones. Take it as a challenge and accept it as part of the process and not interruptions. So it is always important whenever we say face any obstacles, we should take them as a stepping stone and as part of the process in our long goal or journey. Okay, so let us understand the problem statement. This is part of the continuation with the problem that we had yesterday in our daily lead code problem. There exist two undirected trees n and m uh, nodes labeled from 0, 0 to n minus 1 and 0 to m minus 1 respectively. You are given 2D integer arrays edges 1 and edges 2 of length n minus 1 and m minus 1 respectively, where you where I edges 1 of I, A of I, B of I indicates that there is an edge between nodes AI, BI in the first tree, and edges 2 of I, UI, VI indicates that there is an edge between nodes UI and VI in the second tree. And node U is a target to node V if the number of edges on path U to V is even. Note that a node is always target to itself. Return an n integers answers where answers of I is the maximum possible number of nodes that are target to node of I of the first tree if you had to connect one node from the first tree to another node in the second tree. Note that queries are independent from each other. That is, for every query you will remove the added edge before proceeding to the next query. Okay, so one major difference that we see with this problem, or what makes this problem a hard one, is node. Okay, so this is node U is a target if the number of edges on the path U to V is even, right? So in the last problem we just had to maximize the number of nodes, but in this problem they are also asking how we can number of edges on path from U to V is even. So return an array of n integers and maximum. So okay, so this is the whole part that makes this problem hard to understand. So let's look at a few examples to see what we can understand or what is required to be solved from this problem. So there is edges that are defined for the tree 1 and also the tree 2. So and we are at 0th node. Considering the 0th node as this one, we can connect 0th node to the 0th node here, and let's see what are the levels, or let's say this as an even let me color this as, let me mark red as even and yellow as odd, right? So let's call this even set of nodes, where let's say this is even, and we can say this also even, and let's call this even and this as even, because all of these will be in the odd row, right? So if this is even, this is also even, and all of these next set of values will be odd. So this will be odd, this will be odd, this will be odd, this will be odd. So, and these values are also going to be set of odd values. So when we are marking it with odd and even, what we are actually doing is we are saying uh, 0, level 0, and level 1 and level 2. We are marking them based on the level of the node that they are presenting. So if we look at this node, the node 0, we can see there are three set of even nodes. So 0, 0, 0, 3 in the first tree, and set of 5 values which are connected to this even value, which is the set of values which are 1, 2, 3, 4, 5. So this node has 5 values which are connected to it, and that's the value that we need to consider, right? So as we said, this would take up 3 plus 5, and this would be the value that we see here for the node 1. Similarly, let's look at the node 1, and for the node 1, we see there are 3 even nodes in the tree 1, and to the node 4. So let's say we connected to the node 4, or this part of the value, we would be having even set of values which are 4 in number. So 1, 2, 3. Okay, so node 1 from first tree to the node 4 from the second tree. Okay. So with node 1, we see that it is at a level 1, which means an odd parity, and we see that 2 is also at the same odd parity. And if we will have to pick a node which connects, which has largest set of values, then it would be even node, where there are 5 even node values, and we connect it with the same node 1 here, and so it would be 2 of this tree 1 and 5 value in the tree 2. So this would be 7. Yeah, that makes it clear. And the same goes for this, where we say we have this also in the odd parity, and the even parity, even value in the tree 2 is 5 in count. So the same goes here. So 2 plus 5, 2 in tree 2, while these would be having 3 plus 5 and 3 plus 5, as we got. So in simple terms, we are selecting all of the values based on the all of the nodes which are in the same level. Let's say this is in even level, so we select the other nodes which are in even level, as we need to edges to connect between them. That makes it uh, a even parity. While if we want to connect to the next set of nodes in the tree too, then we look at the maximum node value nodes which are there in either the level, either at the parity even or parity odd. So so we always need to keep track of parity odd and parity even for both uh, these nodes. And for the max in tree B, we pick the max of either parity odd or parity even. So that's the whole idea. So this is more this is very much similar to the problem that we had, or the solution that we solved yesterday. So let me bring up the code snippet that we used yesterday, and let us understand what changed. So in our yesterday solution, we saw this implementation where we had this piece of line to create an adjacency list for the graphs, and this was our core DFS logic where we had to check based on the k distance, which might be 2 in the example that was given yesterday, where we were only uh, asked to traverse with only 2 edges between nodes, and we had to maximize the number of nodes that can be uh, visited with the value k. And u was the current node and p was the parent node that we were sending in from this piece of line here. And we were calculating the maximum uh, trees that could be found at a specific node in the tree too, with this max tree. And this was our final calculation where we were adding into the results array, right? So one major difference with this piece of question that we have here is if we see, this piece would remain the same while this piece also remains the same. And mostly uh, here we might see some changes, and these are the two pieces that we might see major changes, right? So we, in our new implementation, we might approach it this way, where we might, instead of having to send in just uh, adjacency node, we might also be sending node p, and instead of k we start sending in the level uh, at which the current node is at, and the parity value, and also the count. So these are the set of values that we send as an input to the DFS function. And parity of the specific node could be calculated with level by 2, and we can also get the value of a particular level uh, of a particular parity index. Let's say if the even levels have the greatest count, or the odd levels, right? So that's one check that we would be adding there. And then we would check for all the neighbors uh, and we would apply the same DFS with the same similar logic until we get the final count, or the count value gets populated, right? So um, in this step here, we are going to do quite a few things, where uh, we are going to calculate count of 2, which is for, let's say, odd and even parity values. and we are going to do that with the DFS helper function that we built, right? So we are going to send in the graph 2 and 0 and -1 as the parent node, and parity 2. Initially parity 2 would be an empty set of values that we are going to build. So this would be an empty array which would be filled with all zeros based on the number of nodes. Okay, so let's try adding this piece of solution to our Leetcode, and let's see how we can solve this problem. This is going to help us building an adjacency list for a graph of certain. We just return the graph with the adjacency array that we have. Okay, so let's have a DFS function just about ready before we approach anything. And let's have the set of arguments that we are going to use. Okay, so, and let's start building the adjacency list and also calculate the length for each of the trees that we have. Okay, so let's start with the DFS function. I think it would be here we are going to send in graph1 with so that after the DFS we get the values with the proper count and parity levels at for each node. So parity 1 and count 1. Okay. So once we have this, so it's time for us to. So we take the parity of the specific node that we send into the DFS function, and we calculate the level of the specific parity, and we also increase the count value for either the odd or even nodes. And once we do that, we simply check the neighboring, explore the neighboring set of nodes of the specific graph. And we only do that if it's not equal to parent node, and so that we don't traverse the same node repeatedly, and we send the same set of arguments. Graph, here it would be neighbor, and this would be the node that we came from, and the level will be level plus 1, right? Parity will be the parity value which we would continuously evaluate in exploration of further set of nodes. Okay, so that would explore all of the parity values for both the graph1 and graph2, and we would have some set of values here. And now it's time for us to calculate the maximum b, and let's say math.max count to so once we have that, we can use that to build our so we check what parity level it is, the specific node is at, and then we uh, add the result value with the maximum node calculation with the first node, and also the consideration of adding a specific node from the tree too. And we return the result, right? So this should be our solution. So yeah, let's try submitting the solution. And time and space complexity here would be m plus n, so that's the whole time and space complexity. Okay, so malformed arrow. Okay, so this should be an arrow statement. Okay, so I think more, let's see. Okay, that should solve this. Okay, count one. Okay, so we also need to pass in the length of each of the tree. This would be m. Yeah. Okay, so parity is not defined. This is in line number 38. Okay, parity. Okay, so we are checking parity of 1. Alright, so as you can see, the solution gets submitted, and time and space complexity of this type of solution is n plus m, that is number of nodes in tree 1 and tree 2, as we are having to create the adjacency list and also perform DFS operation at the most n times and m times, and there is also one for loop which adds up to 2n, but yeah, constant can be ignored, and n plus m is the time complexity and space complexity. If you found this video helpful, please like and subscribe to my channel. Thank you.